Hi everyone, today we have Noam Razin from Tel Aviv University telling us about his paper about the ability of graph neural networks to reason about the interactions between vertices. And with that, let's get to him.
Hi everyone, I'm Noam Razin. I'm a PhD candidate at Tel Aviv University. And first off, thanks for hosting me at this wonderful reading group. And please feel free to ask questions throughout the talk. I'll also stop for questions in fitting places, but you can interrupt whenever you have a question. What I'll present today is a recent work where we analyze the expressivity of graph neural networks in terms of their ability to model interactions between vertices. Our theory also has a nice application to it, which I'll also present. This work was done in collaboration with Tom Verbin and my advisor, Nadav Cohen. I'll start by setting the stage just to make sure that we're speaking in the same language here, though to this audience, I'm sure that the next couple of slides will not be new. Graph neural networks, or in short, GNNs, these are simply neural networks that are designed to operate over graph structured data. Intuitively, their purpose is to model interactions over graphs. Graph data, this is something that comes into play in many different application domains. For example, molecules, these are graphs. The atoms are vertices, the bonds between them, these are edges. And typically, we want to make a prediction over the graph, okay? Say whether the molecule is toxic or not. So these sort of tasks are called graph prediction tasks. We get, as a training set, many different graphs or multiple graphs, and then we train a GNN such that given a new graph, we can make a prediction over it. Another common use case is social networks. There, the vertices are users or items, and edges, these are relations between them. Here, instead of making a prediction over the whole graph, we often want to make a prediction over each of the vertices separately. And accordingly, this task is called vertex prediction tasks. So here we'll have just one large graph typically, and we'll get labels for a subset of vertices, and we'll train a GNN so that we can predict the labels for other vertices. So graph and vertex prediction, these are two common paradigms in which GNNs are used. And besides these specific examples of molecular data and social networks, in recent years, GNNs have been successfully applied across many different applications, whether it's recommender systems or estimating time of arrival, and many more. As a result, there's a significant interest in developing a mathematical theory behind them, so we can better understand why they work and their limitations. And when we have a better understanding, perhaps we can give some theoretically backed practices. One of the fundamental questions that such a theory should address is expressivity. Given a GNN architecture, which functions can we express using it? In other words, say that we have the set of all functions over graphs. We would like to characterize out of these, which we can express using GNNs. To be more precise, from a practical perspective, what we really care about here is the functions that we can express using GNNs of practical size. Because in the end, these are the networks that we can run in practice. In recent years, the expressivity of GNNs has been studied quite a lot, and existing analyses largely fall into three categories. Okay, there are some that fall outside of it, but most of them will be covered by the following categories. So the first one, and by far the most popular, are those that look at their ability to distinguish between non-isomorphic graphs. Two graphs are said to be isomorphic if they're the same graph up to a different labeling of the vertices. We say that GNN can distinguish between two graphs if it can produce different outputs for them. And it cannot if no matter which weights we use for the GNN, it will always produce the same output over the two graphs. So works along this line, they characterize for different GNN architectures which classes of graphs they can distinguish between. And this is done typically by equivalence to classical graph isomorphism tests. Another common line of results is proofs of universality. There, often people show that given a sufficiently large network, wide and deep, then we can approximate any continuous functions over graphs, but possibly up to limitations in distinguishing some classes of graphs. Okay, this is very much related to the first line of works, because some GNNs can distinguish between two graphs, so they can be universal, but up to the fact that they will always output the same prediction over these graphs. Now, the last popular category are works that examine whether GNNs can or cannot express certain structural properties of the graph, okay, whether they can compute shortest path or the diameter of the graph, and so on. Importantly, these functions, they do not depend on features that the vertices might have, only on the properties of the graph. despite this recent progress in understanding expressivity, there's still several limitations to what we know. First is that,
Noam,
are there any questions?
Maybe get to a question?
Yes, of course.
Come on.
Yes.
You're still muted.
Sorry for interruption, but I was wondering about this first property you mentioned, that if two isomorphic or two graph produce different results, they are somehow, but sometime, please correct me, sometime it happens that two similar graph can produce different results because of different algorithm or some different computation process.
So is the question about what it means for or to be able to distinguish non-isomorphic graphs, or what isomorphism even means?
Yeah, I mean, mathematically, this is very straightforward to understand, but if you can just add your clarification from computation point of view.
Yeah, so just to reiterate the idea, so two graphs can be not the same, meaning they're not isomorphic, but it turns out that certain GNNs, no matter which weights you use for them, they will always output the same prediction over them. This is sort of a limitation of the architecture, of a common architecture used. Okay, so this is these characterizations in this field. They typically show which graphs you can or cannot distinguish between. I hope that makes it a bit clearer. If not, please let me know.
It's fine. I think we sometimes the graph structure is so large that it is just my assumption. This lemma, if I can say that, this lemma may not satisfy.
Right. So this is a theoretical results for some graphs. And indeed, it's a question whether the graphs that you have in practice, you do encounter this problem or not. I think there are some cases, for example, in molecular data where two molecules, you can't distinguish between them in terms of their structure, but maybe in other cases, it's not as big as a problem. So that's definitely a question.
So are there any exceptions which you can give, for example?
Exceptions in terms of
like
what?
Where this lemma or where this property just violate?
Where you can distinguish between the graph? I think, for example,
I mean, according to first point, this property may violate very often if it comes to large graph data and computation of those large graph data. So just I was thinking if this can be more.
So this
clear.
very much depends on the structure of the graph. So there are graphs where you cannot distinguish, and there are graphs in which you can. And this is something that can show. This is a theoretical result. So, but this will not be our focus. So I think perhaps it's better if we.
Yeah, I understand. This is like something cannot be.
Yeah, maybe Toma, I'll send a paper into the chat that talks about that. And I think that will be very helpful. Or, well, probably the best is you look at these references here that Noam already pointed out.
Yeah, that
cool.
would be helpful. Yeah.
Thank
you very much. Please.
No problem. It's very much orthogonal, though, to what I'm going to show. So it's not critical to know these results or anything for this.
Yeah, that's perfectly fine. Thank you. Yeah. Thank you.
Great. So, as I said, despite these recent progress, there are still several limitations to what we know. And one limitation is that many of these analyses, they treat this asymptotic regime where the network is allowed to be arbitrarily large, okay, an unbounded width or depth. In particular, this is true for analysis of universality and distinguishing between non-isomorphic graphs. Hopefully, we would like to get a more fine-grained characterization of what we can do with finite-sized GNNs. Another limitation is that we lack formalization for the ability of GNNs to model interactions between vertices. And intuitively, this is what we use them for. What I mean by that, in other words, is that given an input graph and features for the vertices, we can view the GNN as a function over those features. And we would like to be able to characterize how does the graph structure and the GNN architecture affect the type of functions that we can express with respect to those features. In particular, which types of interactions we can model. And this is exactly the gap that we aim to address in our work. We tackle the question of how does the graph structure and the GNN architecture, specifically its size, affect the interactions that it can model for some formal measure of interactions, which I'll introduce in a couple of slides. So what am I going to show today? Okay, we're going to have two parts. The first is a theoretical analysis, In the second, it's going to be a practical application of it. Another name for this slide is the why should you care or why should you listen slide. This is what I'm going to elaborate on in the remaining of the talk. So first, the theory part. We're going to formally quantify the ability of certain GNNs to model interactions across the partition of vertices in a graph. We're going to do so using a formula in the measure known as separation rank, which has origins in physics. I'm going to spoil the surprise and say that for a given input graph, such as the one that we see here, and a partition of its vertices to blue and red vertices, then what we're going to see is that the ability of a GNN to model interactions between the blue and red vertices, it's going to be primarily determined by the number of walks that originate from the boundary of the partition. Okay, these are the vertices in gray here, the vertices with an edge to the other side of the partition. Okay, I'll say it again. The main result is going to be that the strength of interactions that these GNNs can model, it is primarily determined by the number of walks of a certain length that depends on the depth of the GNN, originating from this boundary of the partition. Then we're going to use this characterization for a practical application. We're going to design an edge specification algorithm which aims to preserve the ability to model interactions as we remove edges from the graph. The idea is that if we have a very large graph, for example, a social network, then running a GNN over it can be quite expensive in terms of memory and compute. And so one way of addressing this is to try to remove edges from the graph while attempting to maintain the prediction accuracy that we can get. And it turns out that our theory, it will lead to a very simple and efficient algorithm for removing edges, and it will outperform actually alternative methods, at least those that we tried, in terms of the prediction accuracy that you can get over the sparsified graphs. Okay, so basically we're going to quantify the ability to model interactions theoretically, and then use it to derive an edge specification algorithm, which will allow us to achieve high performance over sparsified graphs. Okay, now I think it's a good time to stop for questions. So before I delve into more details, are there any questions about the introduction thus far?
Will we have connections to the bike connectivity paper? Do you know what I mean?
Yeah, so I'm familiar with the paper, and actually, no, some of the names, they seem similar because also there you have cuts in the graph, but in terms of theory there, correct me if I'm mistaken, but they analyze structural properties of the graph, whether you can compute, for example, certain vertices, whether they're on the cut or not, if you remove them, whether you create two connected components. And here we're going to talk about how the function looks like with respect to the features. Okay, so that topology will affect the type of function you can realize, but we will view the function with respect to the features.
Yeah. Okay, thanks. Makes sense. Does sparsifying graphs actually help scaling up GNNs? That's a question we have in the chat.
So that's an excellent question. So we'll see in the experiments that you're able to get high performance, even if you remove, for example, 60 or 80% of the edges. And whether this is a bottleneck or not, in practice, this depends on your use case. Okay, if you have a very large graph, then yes, it does make you run faster, training and inference. And whether it's a problem or not, it depends on how large your graph is. So yeah, very much. If someone here is working on graphs, for example, on the scale that you have in industry, it will be very interested, for example, to talk with, to better understand whether they have these problems there as well.
All right. So the perfect question to add in onto the promo section.
Yeah. Okay, so are there any questions?
I don't think so.
Great. So let's move on and we'll start with the theoretical part. And first up, let's define the formal measure of interactions that we're going to use, which is called separation rank. This is a known measure, which for a given function, it measures how strong are the interactions that it models across a partition of its input variables. Say that we have some multivariate function f. It has n input variables. Each one of them can be a d-dimensional vector. Now, a subset of its input variables I, this determines a partition of the variables into those in I and the remaining input variables. Here in the illustration, I is just the first half of the input variables, but of course it can be any arbitrary subset. The separation rank of f with respect to I, it measures the strengths of interaction that f models between xi and xi complement, and it is defined as follows. It's the minimal R such that we can express f as a sum of R terms. Each one of them is a product between two functions, a function that only operates over xi, and a function that only operates over xi complement. Okay, what does this mean? Okay, first off, the higher the separation rank, the stronger the interaction that F models between xi and xi complement. Intuitively, how you can parse this? These G functions, they can be arbitrarily complex, G and G bar, but they can only operate either over xi or over xi complement. And then in order to express F, we need to combine them using a simple function, okay, a multiplication and a sum. So the higher the separation rank, the higher this R is, the more terms we need, the more complex this combination function needs to be in order to realize F. Okay? In a sense, the stronger the interactions that it models. Another interpretation is that if the separation rank is equal to 1, then the function is separable. It can be implemented as a product of two functions that operate over two different parts of the input variables. In a statistical setting where F is a probability density function, this exactly means that xi and xi complement are statistically independent. Okay, and the higher the separation rank, the further you are from this situation. Now, this is not a new measure, as I said, and it has several usages across the sciences. One common usage is in physics, where it is known as a measure of entanglement between particles in a many-body system. More relevant for our purposes, though, this measure was already used for analyzing other types of neural networks, whether it's convolutional, recurrent, or self-attention neural networks. And here we'll see how we employ it for studying graph neural networks. Now we have our formal measure of interactions in place, and we're going to define which GNNs we're going to analyze. And these are going to be a type of message passing GNNs. So this is one of the most common family of GNNs, where the idea is very simple. Okay, so we have an input graph to the GNN, where each vertex is associated with features, okay, with a feature vector. The message passing GNN, it associates each vertex with a hidden embedding, and then at each layer, it updates the hidden embeddings according to the neighbors of the vertex. A one-layer message passing GNN, computing the embedding of A, looks something like this. Okay, first you take all its neighbors, you do some transformation over their embeddings, and then aggregate this to get a new embedding for A. And if you have another layer, then these embeddings themselves, they're an outcome of a GNN layer. To be more mathematically formal about it, then initially we set all the hidden embeddings to be simply the features of the vertices. And then a common update rule at each layer of the message passing GNN for a vertex I is the following update, where you go over all of the neighbors of I, you do some transformation of the hidden embeddings from the previous layer. Here it's simply a linear transformation. And then you aggregate these vectors that you get into a single vector. And that's your new embedding for vertex I. Different GNNs, they differ in terms of the transformation that you do and the aggregation function. For example, probably the most popular GNN to date, the GCN, the graph convolutional network, it is obtained from this formula if you take the aggregation function to be a weighted average followed by a ReLU nonlinearity. After L layers of this GNN, you get hidden embeddings for each of the vertices. And what you do with them really depends on the context. So in graph prediction, where you want to make a single output for the whole graph, then typically what people do is you again aggregate all these embeddings into a single vector, and then you have a linear output function. In a vertex prediction setup, where you want to make a prediction over every vertex T in the graph, then you can simply use this linear output layer over each of the vertices separately to get a prediction. Okay, this is just standard message passing GNNs up until now. Our goal is to investigate their ability to model interactions between vertices. And prior works that did so for other types of neural networks, they focused on neural networks with polynomial nonlinearity. And they used the fact that you can actually represent these neural networks as certain tensor networks. Okay, tensor networks, this is a graphical language for expressing arithmetic operations known as tensor contractions. This is sort of generalization of matrix multiplication. Their exact technical definition is not really important, but what suffices to know is that the computation graph of these neural networks with polynomial nonlinearity, they can be represented as this graph on the right, where each node is a tensor and edges they represent contractions, arithmetic operations. And this allows to use tools from tensor analysis in order to analyze the interaction that these networks model. A natural question that may be thinking is, well, why should we care about these neural networks with polynomial nonlinearity? Because in the end, they're less common in practice as opposed to other variants, for example, with ReLU nonlinearity. And while it's true that they're not as common, I believe they do have significant interest. And this is for several reasons. The first one is that although they're not state-of-the-art in many cases, they still have shown competitive performance in practice. So this is not just a theoretical construct. These networks can actually work. The second is that they're also compatible with several future technologies, such as quantum computing. This is partly due to their correspondence with tensor networks. But more importantly, for our purposes, is that their theoretical analysis has led to numerous insights, which were then demonstrated empirically on other variants and more common networks. And this also led to development of practical tools for just widespread deep learning models, okay, not just neural networks with polynomial nonlinearity. So from our perspective, this is more of a theoretical survey. We're going to analyze these neural networks and then show through experiments that indeed the predictions that we get are faithful to what we have in practice with more common variants. Okay, this is what previous works have done for other neural networks, and we're going to follow this blueprint. Essentially, we're going to study GNNs which have product aggregation. This means that the function that they realize over the feature of the vertices is polynomial. Okay, so what it means is that if we go back to our update function in the message passing GNN, then the aggregation function will be just an element-wise product. And indeed, similar to previous works, we can show that you can now represent the computation graph of this GNN as a certain tensor network. It's a bit more complex of a tensor network. Specifically, now the computation graph depends on the structure of the input graph to the GNN, but it's a similar equivalence. And although these neural networks are not as common in practice, as opposed to, for example, GCN or other GNNs with ReLU nonlinearity, this actually turns out to be a variant of a recently proposed GNN, which has shown competitive performance. But more importantly, again, is that we're going to see that the predictions made from the theory, at least empirically, they also apply or are faithful to other GNNs with ReLU nonlinearity, and we're going to use it to derive our edge sparsification algorithm. Okay, so this was a bit of a mouthful, but now we have our model in place and the measure of interaction, separation rank, with which we're going to analyze it. And before I move on to the main result, are there any questions about the setup? Okay, so I hope everything is clear, but please feel free to interrupt me. So now we're going to characterize the strength of interaction that these networks can model across a partition of vertices. And the quantity that is going to be important here is what we call the walk index of a partition. For a given graph in a partition of its vertices, okay, here we have a subset of vertices in blue, that's I, and a subset in red, this is the remaining of the vertices, I complement. Let's denote by Ci the boundary of the partition. This is the vertices that have an edge to the other side. Then, given a depth L GNN, we define in the context of graph prediction the L-1 walk index to be the number of length L-1 walks that originate from the boundary of the partition. This is a very straightforward definition. I'll say it again. Okay, the L-1 walk index of I, okay, of the partition that it induces, is just the number of length L-1 walks from the boundary of the partition. For example, if we have a depth 3 GNN, then the 2 walk index, this is going to be length 2 walks. So for example, we have the walk that starts here and goes to this red vertex and then back to here, or a walk that starts here, goes to here, and then to here. I think in this graph, there are 48 walks of length 2 that originate from this boundary. In the context of vertex prediction, we have an analogous definition, but now if we make a prediction over a target vertex T, then the L-1 T walk index of I, this is simply the same definition, but we only consider walks that end at the target vertex. Okay, so it's the number of length L-1 walks from the boundary of the partition that end at the target vertex T. All right, so now we have this definition of walk index, and it seems a very fundamental quantity. And actually, we were quite surprised to not find an existing name for it. So we named it walk index. And with this definition, our main result is a characterization with a separation rank of the depth L GNN with which the H with respect to a subset of vertices I, okay, with respect to a partition that it induces. And what we prove is that in the context of graph prediction, the separation rank, okay, the strength of interaction, it is upper bounded by the width to the power of the L-1 walk index of I. In vertex prediction, we have the same result, but in the exponent, instead of the L-1 walk index, we have the L-1 T walk index, okay? Now we consider only walks that end at the target vertex. These are upper bounds, but we also have nearly matching lower bounds, okay? They're not exactly tied, still for example, instead of the width in the base, we have a slightly different constant, but they are relatively tight, okay? They're nearly matching. Now let's try to parse what's going on here, okay? First, notice that you have here a dependence on the quantities that we wanted. We have here the width of the network. We have a polynomial dependence on it. We have the depth. This determines the length of walks that we examine. And we have the structure of the input graph. Okay, it comes into play in terms of the walk index, the number of walks from the boundary of the partition. And what this means is that given that we have some fixed size GNN, what's going to be important in order to model interactions between a partition of a graph is exactly the number of walks from the boundary of the partition. Okay, the strengths of interactions are primarily determined by this walk index. Also, it appears in the exponent, whereas we have only a polynomial dependence on the width. Okay, so before I move on to the implications, just to give a bit of an idea where the proof comes from, I will go over a brief proof sketch. Okay, this is just for those who are interested in the more technical details, but of course, the details here in this slide, they will not matter for the rest of the talk, and will continue afterwards with the more high-level implications. The main idea behind our upper bound, this is just for graph prediction because the result for vertex prediction is analogous, is to use this correspondence between GNNs with product aggregation and tensor networks that I mentioned before. Okay, essentially, we can represent the computation graphs of these GNNs through this graph, okay, this tensor network, where each node is a tensor and edges, they represent contractions, okay, these arithmetic operations. Okay, so this is not to be confused with the input to the GNN. Okay, this is the computation graph of the GNN itself. The leaves in this tensor network, they correspond to vertices in the original graph. Okay, essentially, each one of them corresponds to a feature vector of one of the vertices. The interior nodes, these are the GNN layers. They embody the operations that it performs over these features. And the main idea is that once that we have this representation, then we can use tools from tensor analysis in order to show that the separation rank of our GNN, okay, the strength of interactions that it can model, is upper bounded by minimal cuts in this tensor network among the cuts that separate the leaves that correspond to vertices in I, from those that correspond to the other vertices. Okay, so I'll just say it again more slowly to make sure it's clear. Then we want here to bound the separation with respect to I, which is a partition in the original graph. Okay, this is a subset of vertices in the input graph to the GNN. And it turns out that we can upper bound the separation rank, but looking at cuts in this computation graph, where these cuts, they separate the leaves in the tree, which correspond to these vertices in I in the original graph, from the vertices that correspond to the other vertices in the original graph. And then the proof concludes by finding such a cut whose weight is small enough. Okay, essentially, its weight, it's exactly the upper bound that we see in the theorem. And that's it. The lower bound is a bit more technical, and I won't go into it in this talk. All right, so now let's go back to a more high-level view and discuss the implications of these results. And one straightforward implication is that if we have a graph and two partitions in the graph, okay, so both of these graphs that we see are exactly the same. It's two clicks connected by a single edge. On the left, we have a partition that separates the two clicks, and so it has a low walk index. The boundary of the partition only includes two vertices, and so relatively, compared to the partition that we have on the right, its walk index will be low, okay, because on the right, what we have is that each click holds half of the vertices from each partition, and so all of the vertices are on the boundary here, and it has a high walk index. What our theory tells us is that GNNs, they can only reach low separation rank with respect to the partition on the left, whereas they can have high separation rank with respect to the partition on the right. What this means is that they can model stronger interactions across partitions that have a higher walk index. Intuitively, this formalizes conventional wisdom by which GNNs can model stronger interactions across areas of the graph that are more interconnected. This word, interconnected, it's often used informally, and our theory suggests that perhaps a good interpretation for it is the walk index, the number of walks from the boundary of the partition. This theorem is for GNNs with product aggregation, but what it suggests more broadly is that if we look also at other types of GNNs, and we have two types of data sets. In one of them, we need to model interactions across a partition which has low walk index. And in the other, what's important is interactions across a partition with high walk index. Then, what our theory suggests is that we should get better performance over data sets of the second type, okay? If we need to model interactions across partitions with high walk index. Okay, so to say it again, we expect from our theory that GNNs will perform better in practice on data sets that require stronger interactions across partitions which have a higher walk index. And to see if this is the case indeed, we run experiments. We take standard GNNs with ReLU nonlinearity on two control data sets, where in one of them you need to model interactions across a low walk index partition, and in the other you need to model interactions across a high walk index partition. Now, there are many cases in which you can think of how to do this, but the setup which we came up with is the following. So both data sets, this is the graph prediction task, and the goal is, given a graph, you predict whether two fashion NS images that are encoded in it have the same class or not. What this means is that for each graph, we randomly sample two fashion NS images, then we take patches of pixels from them, and we put them as the features of the vertices. The label of the graph will be 1 if both images are of the same class, and 0 otherwise. In both of the datasets, all graphs have the same structure. And this is exactly the structure that we saw a slide before. It's 2 clicks connected by a single edge. On the left, this is an example from the first dataset, and on the right, this is a sample from the second dataset. What differs here is what you see in the colors. It's how we assign the patches of pixels of both of the images to the vertices of the graph. In the first dataset, each click holds all of the patches from a single image, whereas in the second dataset, each click holds half of the patches from the first image and half of the patches from the second images. If you run a GNN, in order to solve this task, it needs to model strong interactions across the partition that separates the two images, okay? Because it needs to say whether they're the same class or not. What this means is that on the left dataset, it needs to model interactions across a partition with a low walk index, right? This is exactly the partition that we saw before. Whereas on the right, it needs to model interactions across a partition with a high walk index. What this means is that we expect GNNs to work better on the dataset on the right. And this is indeed what we see in practice. Okay, so the exact numbers in this table are not super important, but we ran here 3 of perhaps the most popular GNNs today. Okay, the most standard GNNs there are, the GCN, GAT, and GIN with ReLU nonlinearity. And here you see both the train and test accuracy that we get over both of these datasets. And in all cases, we see that we get a significantly higher accuracy over the dataset with a high walk index partition. The bottom line here is that in accordance with our theory, we see that in practice, GNNs do perform better on tasks where you need to model interactions across partitions with a higher walk index. Okay, at least as verified by these controllable synthetic tasks. This concludes the theoretical part of the talk. And before I move on to the practical application, are there any questions on it?
Not from my side.
Okay, great. So let's move on. And now we're going to use the theory for deriving an edge specification algorithm, which preserves expressive power in terms of the ability to model interactions. So the main idea here is that, say that we have a very large graph, then performing computations over it can be quite expensive, both in terms of memory and compute. One way of addressing this problem is edge specification algorithms, which remove edges from the graph while trying to maintain certain properties of the original graph. Different areas of computer science try to maintain different things. In theoretical computer science, often what people care about is preserving the distances between vertices or weights of cuts. In network analysis literature, for example, the statistical properties of the graph, such as the degree distribution, is what's important. And in the context of GNNs, what we care about is maintaining the prediction accuracy that we can get over the graph as we continue to remove edges. What we're going to see now is that our theory is going to lead to a very simple and efficient recipe for removing edges if you want to preserve the interactions that you can get. And it turns out that this will lead to very high accuracies, even on sparsified graphs. So recall what our theory said is that if we want to model interactions across a partition of vertices, okay, between some subset of vertices I and its complement, the key quantity here is the walk index, the number of walks from the boundary of the partition. This leads to a simple general recipe for removing edges, where the idea is to greedily remove the edge whose removal will harm the interactions the least. And we check that through the walk index. To exemplify our algorithm, let's focus on this graph. And what's going to happen is that at each iteration of the algorithm, we will remove a single edge. And what we do in each iteration is, first, we need to decide across which partitions we want to preserve the ability of interactions. Okay, this step, it requires some prior knowledge about the nature of the task at hand. For the sake of example, we'll assume that we need to model interactions across the left and right side of the graph and between the top and the bottom sides. Then, for each of the edges in the graph, we'll temporarily remove it and compute what the walk indices of these partitions will be once that edge is removed. Starting from the first edge, we remove it. Then we compute the walk index with respect to the first partition, and then with respect to the second one. This gives us a tuple. Here it's a pair of walk indices. Then we add the edge back and move on to the second edge. And again, do the same thing. We compute the walk index with respect to the first partition, with respect to the second one, put it back in. In the end, we get a tuple for each of the edges in the graph. Here it's 8 edges. And the edge that we remove is the one whose walk index tuple is maximal, according to some order over tuples that we define. Okay, this is also something that we need to define. For example, we can order them by their sum or by their minimal entry. And here, let's say that, for example, it's this edge. And then we remove it completely and continue on in iterations. Okay, so this is a general scheme. And in order to cut out a specific algorithm from it, we need to decide on two things. First, on which partitions we want to model interactions across, okay, preserve the strength of interactions for. And second, an order over tuples. And once we define these two, we get an algorithm. In our work, we propose the following instantiation, but of course, examining others is also interesting. And this is an instantiation that focuses on vertex prediction tasks, because these are often relevant in large graphs, for example, as social networks. The algorithm is called the L-1 Walk Index Sparsification, or WS in short. L-1 stands here for the fact that we're going to use walks of length L-1, okay, the L-1 walk index. So this is dedicated for maintaining the ability of depths L GNNs to model interactions. So in vertex prediction tasks, we make a prediction over each of the vertices separately. So we want to model interactions between the vertex and the remainder of the graph intuitively. Okay, for each vertex, if we want to make a prediction over it, then we better be able to model interactions between it and all other vertices. And so I claim that it's natural to look at the partitions that exactly separate each vertex from all others. So the number of partitions that we have here is exactly the number of vertices in the graph. Then, without any further knowledge, the prediction over each of these vertices is equally important. So we'd like to not remove an edge, which will harm significantly the interactions that we can model across one of these partitions. We want to make these balanced removals. And so what we do is we order the walk index tuples according to their minimal entry. And then we break ties using the second smallest and so forth. What this means is that we remove the edge whose minimal walk index is maximum. So just to complete the picture, what the algorithm is doing, for each edge that we want to remove, we'll compute walk index tuples for all of the edges. Okay, we'll compute what the walk indices of these partitions will be after we remove that edge. And then we end up removing the edge, which has a maximal minimal walk index. Okay, and break ties using the second smallest and so forth. And that's it. That's the whole algorithm. Are there any questions about it, perhaps?
Yeah, how do you compute the walk distance again? So, and what's the intuition of walking distance of order L?
Great. So it's the walk index, it's the number of lengths L minus, the L minus 1 walk index is the number of lengths L minus walks from the boundary of the partition. For example, for this partition, it's going to be the number of walks from these three vertices of length L minus 1. One way to compute this is you take the adjacency matrix and then you take it to the power of L minus 1. Now, indeed, you might say that when you have a very large graph, then this is an operation that is cubic in the number of vertices, right? You take an n by n matrix, okay, number of vertices by number of vertices matrix, and you need to take powers of it. This can be quite expensive as well, even though it's a very fundamental quantity. And so actually, it turns out that if we look at 1WS, okay, the specific version for a depth 2 GNN, then it has a very simple and efficient equivalent form, which only depends on degrees of vertices and is much more efficient. And all you need to do in order to compute these removals is at each iteration, you compute the degrees of the vertices. You can also do this once at the beginning and maintain the degrees. And then you just remove the edge which has a maximal minimal degree. Okay, the minimal degree of the edge, this is the minimum between the two degrees. And you can break ties using the maximal degree of the edge. And that's it. So I kind of continued with the talk while answering the question, but yeah, if there are any more questions about the algorithm, now is a good time just to already show that yeah, indeed, computing the L-1 walk index sparsification can be quite expensive when you get to large graphs, but this algorithm is very efficient. It's a sort of, you can view it as an efficient approximation to it.
I guess the question had great foresight, but Francesco is now following up with what's the reason we are interested in the number of walks, or like why is this an especially relevant quantity for your graph?
Right. So this comes from our theory. This is the reason that we looked at it. So our theory recalled that if you want to model interactions between a partition of vertices, then the theorem says that what primarily determines the strength of interactions is the walk index. It's the number of walks from the boundary of the partition. And so here we propose an algorithm that, given that you decide on which partitions you care about, here we decided these partitions to be exactly those separating a vertex from all others. Then if you want to maintain the ability to model interactions, then you should try to maintain the walk index. And this is exactly what the algorithm tries to do. And now, whether it performs well in practice, this is what we're going to see in the evaluation in the next slide. Okay, so are there any more questions about the algorithm?
No, the additional questions in the chat you already excellently addressed with this slide.
Great. Okay, so just before I jump to the evaluation,
I guess then just now we got a question with Zhong Xu, I think. Can you explain again how the tuple is constructed?
Sure. So this is from this slide. Okay, so I'm not going to go through the whole animation again, but the idea is you temporarily remove an edge from the graph, and then you just compute the walk index. Okay, you compute you have the adjacency matrix. The walk index is just the number of walks of a given length from some vertices. So you can take the adjacency matrix. You can take a power of it, the L-1 power of it. This gives you for each vertex the number of length L- walks to any other vertex. And then you can just sum the relevant entries. And that's how we compute these tuples. So we have for each the tuple, it contains the walk index for each of the partitions that we care about. For example, in our algorithm, these are the partitions that separate a vertex from all the others. Okay, so in this algorithm, you have exactly the number of vertices partition, you have this tuple, and then you remove the edge, which has the maximal tuple, meaning if you remove it, you still have high walk indices.
And then do you know of a question from Nick? Any insights on the number of partitions we need?
So this very much depends on the problem. And here we just gave a specific instantiation. This is a sort of something from intuition that in vertex prediction, these may be the important partitions, but obviously there are many other options you can try. And actually there's no reason to believe that perhaps this is even the best choice. Maybe if you choose a bit different partitions, you'll get a better algorithm, even for vertex prediction tasks. So this is very much something that's interesting to look at. This is just a specific instantiation that we focus on. But any different partitions that you choose, or different ordering, or the tuples, this gives you a different algorithm.
Then for a very large graph, if we have 1 million plus nodes, is it possible to use this method on subgraphs and then combine these metrics / insights in any way?
Yes, exactly. So that's a very good comment. Actually, saved it for me for saying that. These quantities, they're very fundamental, and there are often various ways to compute them. They're very parallelizable. For example, this is just computing the degrees. So for example, if you look at connected components, you can do it separately. You can also approximate these quantities. So it's very fundamental quantities. There are, I think, many methods to compute them efficiently over large graphs.
Okay, and so we also have the question, is it like can you speculate on properties of graphs where this method works better for sparsification than for than if we don't have these properties, like having clear communities or something like that?
Great. So that's a great question. I think maybe I'll go to the evaluation in the next slide, and then we can discuss this. For example, we'll see when it works well on which graphs, and then perhaps we can speculate on why does it work well there. I'm not sure I have an excellent answer for that, but we can think about it. So to evaluate these methods, what we do is we compare them to several existing baselines for removing edges over standard vertex prediction datasets. So the baselines we compare to are first just the naive removing edges uniformly at random. Second is a known spectral sparsification algorithm. Okay, the goal of this algorithm is not to maintain the accuracy of GNNs, rather to maintain the spectrum of the graph Laplacian. Okay, so it wasn't really proposed in the context of GNNs, but we still compare to it as a sort of representative or more classical methods. And the last method is an adaptation of a recent supervised method for learning which edges you want to remove in order to maintain the prediction accuracy that you can get. Okay, this is called UGS. What we're going to do is that we're going to take vertex prediction datasets. Okay, these are graphs where we remove edges using each of these methods and also ours, and train just a standard GNN. Here it's going to be a depth 3 GCN with ReLU nonlinearity. We also have similar results using GIN. We're going to examine the test accuracy that we get over the sparsified graphs. First, let's start with Cora, a really simple data set. This is the fashion MNIST or MNIST of GNNs. Citation network, each node is a paper and edges are citations. What you can see here is in blue, these are our algorithms. So we have both 2 WIS. This is the algorithm which is dedicated for maintaining the ability to model interactions for depth 3 GNNs. Okay, this is compatible with the depth 3 GNN that we use. And we also evaluate 1 WS. This is the efficient approximation version that I showed. Essentially, this is the algorithm for depth 2 GNNs, and it is very efficient. So we use it also for depth 3. And as you can see here, it works just as well. Okay, both of our methods, they reach substantially higher test accuracies throughout the sparsity levels as opposed to the baseline methods. This was a very simple and small data set, but we see a similar trend also when we move on to more larger data sets. Specifically, OGBN archive has already more than 1 million edges. On these, we only evaluate 1 WS because running 2 WS can be quite expensive over these larger graphs. And again, we see that our method leads to higher test accuracies across the sparsity levels. And the bottom line is that our theory led to this WS algorithm, which is both efficient and, I claim, simple to compute, and it leads to high test accuracy. Okay, it outperforms existing methods, at least those that we tried, in terms of the accuracy that we can get over sparsified graphs. And of course, we release its implementation, and we also have a quick start notebook for those who are interested to just take and run it. It's very simple to run, so if you're interested, feel free to do so. So now, maybe if I can try to address the question before, here these are citation networks, where intuitively you do depend on a vertex. If you want to make a prediction, it does help to model interactions or to take into account information from the neighbors. And so trying to preserve interactions between each vertex and the rest of the graph, it sounds like something that should work, and indeed it works well. But interesting enough, we also tried this on graphs. I don't have the experience here that are not it's called homophilic, right? Where each vertex, its label is similar to its neighbors. But this algorithm also worked pretty well on graphs that were not homophilic, okay? Where, for example, these data sets where the label is actually usually different than the vertices.
What do you think it says about our data sets that if we remove, even after we removed all of the edges, we are still getting 70%?
Oh, that's an excellent question. So indeed, there's enough information in the features themselves that you don't need much in order to do relatively well. So indeed, interestingly enough, removing just uniformly at random, it doesn't do so bad, right? You can improve upon it, right? So our algorithm does much better, but it still does decently to remove uniformly at random. And actually, there are graphs that we tried where if you remove at random, then you don't get any degradation in performance whatsoever. So I guess it says something about their complexity and how really model interactions between vertices is important. And here it is important, though, again, it's not that you get random accuracy if you don't use it. Though on the larger edge, you can see that if you don't use any edges, you get around 50% accuracy, which is pretty bad relative to 70%.
Yeah.
Okay, so before I conclude, are there any more questions about the evaluation or the algorithm?
Do you see similar trends when using other metrics like area under the receiver operator characteristic curve?
And that's a good question. We haven't tried actually. We've mainly looked at test accuracy here. Yeah, so it's a good question. I'm not sure.
And credits to that for the question to Remy. And then Anwar is additionally asking, would it then be better to compare with accuracy using without using graph structure? It will tell us how much these features contribute to the performance.
Right.
But what we're interested in here is how much of the performance we can preserve. I'm a bit confused, but maybe Noam.
If I understood correctly, it says that we should also compare to where we have no graph structure. And this is what you see on the right end. This is exactly, you have 100% of the edges removed. This is just, you don't have a graph, okay? There are no edges. It's just based on the vertex features. And essentially you have an MLP performing on each of these vertex separately. And indeed, it turns out there are some data sets in which you can go all the way to the right and you have no degradation in performance, which says something more about the data set than the method.
Okay.
Okay, so I think I'll conclude. And just to recap what we saw, then we started with the theoretical analysis part, where we formally characterize the ability of certain GNNs to model interactions across a partition of vertices in the graph. What we saw is that the walk index, this is the key quantity that controls the strength of interactions that we can model, okay? The number of walks of a certain length from the boundary of the partition. We then use this theory to derive an edge specification algorithm called WIS, which aims to preserve the ability to model interactions. This algorithm is simple, it is efficient to compute, and we just saw that it outperforms alternative methods that we tried. So this is what we saw today. And if we look more broadly going forward, then we use this framework of model interactions to study expressive power, okay? Which interactions can the GNN model? But perhaps we can also use this to study other aspects beyond expressivity, such as generalization, meaning not only which interactions can the architecture model, but what do we get in practice when we run gradient descent over the GNN? What does it learn? What is the strength of interactions or the function that it ends up learning? This is in terms of the theory, but also in terms of practice. Perhaps we can use this framework to try and improve the performance of GNNs. Here we saw one practical application of an edge specification algorithm, but maybe in the other direction, perhaps we can try to add certain edges to try and improve the performance that we can get. Or maybe we can try to design, based on the theory, different GNNs that can model stronger interactions. So I think there's many other things that you can do with this framework. and hopefully can lead to other fruitful insights and applications. And with this, I'll conclude. So again, thank you very much for your attention, and I'll be happy to answer any more questions.
Okay, great. Yeah, thank you for the insightful presentation and all of your answers already. But we definitely have some more questions also from the chat, because Young Shu is asking, have you measured how long does the walk index take to generate the sparse graphs?
Yes, so on the largest graph, which is the OGBN archive, it's more than 1 million edges, and it took around, I think, an hour and a half. But this is something that you only run once, and then you can just use it however times you want. So you run it once before you run a GNN over it, and then you only need to run a GNN over the sparsified graph.
Yup. And then did you test the method for smaller graphs? Like someone is interested in sparsification for molecular graphs, but there I'm also not so sure how relevant it is actually to do sparsification for smaller graphs.
Yeah, so I guess it depends. I'm not sure what the motivation is, because in terms of, I guess in terms of runtime and complexity, this is maybe not the issue, but maybe if there's some other intuition why you want to sparsify, then you can use the same framework to design an algorithm for it. This is possible, but we haven't thought about it.
So, but then I want to the comment from Remy. Apparently, Remy they have observed that the rock AUC, when removing all edges, is not impacted much by removing all of the edges. So I'm not sure what sort of graph data set he or she is talking about.
Yeah, so it's interesting. I guess maybe I wonder if it's because we did see this as well on some of the graphs, but not on those that I showed. So it's interesting. Maybe afterwards to try and understand.
So do you think it is likely possible to approximate higher order L walk index?
Yes, I think so. You need to compute walks of a certain length. And I think it is possible, but also I'm not sure. In the end, we saw in the experience, at least on the core data set, that we get a similar performance. So I'm not sure if it's worth it, but I guess so. Yes, you can parallelize the computation. There are various ways in which you can make it faster. We haven't totally optimized it.
Okay, and that was a question by Leroy. And yeah, Rishabh also brought this up already or something in that direction, but I wanted to, do you have any thoughts about understanding over squashing and the edge? Well, at least they remove some edges as well. They don't do sparsification and don't remove a large amount of edges, but there they also have their algorithm based on the Ritchie curvature and calculating the Ritchie curvature for removing edges or adding edges to alleviate bottlenecks.
Right. So
you see any connections, or connections of how we're changing the properties of the graph when we're only removing the least interacting edges compared to using something like curvature to add and remove edges?
yes, so at least in terms of a direct relation, it's not something that I'm aware of. It's possible that there is some connection.
But I mean, the thinking there is somewhat, or must be somewhat, I think, if we have a bottleneck and we have interacting or strong interaction, or kind of, you can only have strong interaction if you don't have a bottleneck, or is that true? Is that not true?
I think, I'm not sure whether you can show such a thing, at least not off the top of my head, but in terms of the algorithm itself, of the removing edges, then they may be similar in the sense that, if I recall correctly, then this edge specification or rewiring based on curvature, then essentially you have negatively curved edges, yes, where you have multiple edges into a single bottleneck, then you try to change that. And when you remove edges according to our algorithm, you'll try to refrain from having a single vertex where you just eliminate all of its edges. So it will also lead to maybe something similar, but it's not a very direct connection that I see, but I think there may be one.
Okay, but still interesting directions to think into.
Yeah.
And I guess the audience may do that. Everyone may do that. Otherwise, I would just, we have no more questions in the chat. And then I would say we have a very timely hitting the mark of the hour session today. But then we have another follow-up. Does the WIS method know when to stop in terms of removing edges?
This algorithm. So yeah. Here you need to pre-specify essentially. What we showed is that essentially you can just continue removing edges until you want, and we show the accuracy for each sparsification level. So I guess you need to determine, depending on your budget, how many edges you want to try to maintain. So this is something that you need to specify. You can say how many edges you want to keep.
But if you want to preserve a certain level of accuracy, yeah, but probably the thing that you want to go for is how much compute do you have, how much do you need to sparsify?
Yeah, exactly.
But John, do you want to unmute?
Yeah, hi. So can you hear me?
Yes.
Yeah.
Cool. First, thanks for the great talk. And I still have some questions on the runtime of the sparsification algorithm, because you mentioned that on the OGBN archive, I think you take like 1.5 hours to essentially run through the sparsification. So my question is, have you compared, let's say, look into the convergence time of the sparsified graph compared to the original graph? So let's say, suppose you begin to measure the time when, like, for both the convergence of the GNN model itself and also the time you need for sparsification, then I'm wondering whether it actually accelerates the whole training process if you consider both of the time together. Let's say compared to if you do not do the sparsification but you train on the original graph. And that question makes sense to you?
Yes, of course. So first off, after we sparsify the graph, then indeed we see that we are able to train faster. Though in order to really see a big difference, perhaps you need to go into larger scales. Though I would note that we take 1.5 hours over the OGBN archive, but this is really not optimized in any way. Okay, you can parallelize the computation and do all sorts of stuff. You just need to compute the degrees, and there are many ways to do this faster. We just compute it naively. And another thing is that once you sparsify the graph, you only do this once before training. Then you can use the graph as many times as you want, train as many models that you want, run cross-validation, different GNNs. And so indeed, I think it can save you time. But it's true that in order to really verify the usefulness of this in practice, you need to go to maybe even huger graphs, industry scale. There it also has the benefit that if you have a sparser graph, then you can fit more in a GPU. Okay, you can have larger batch sizes because the neighborhoods of each vertex is small. So this is something that very much needs more research to verify.
I see. Yeah, I think that makes sense. Yeah, I'm just wondering, like, let's say if there's some results of the time of the convergence after the sparsification, and also, let's say, or the training time after the sparsification, and also the time needed for the sparsification can be included. I think, that may be more informed, like provide more information to like people who use the approach, I think. But I think this is very interesting because, yeah, I think this is definitely very important to industry, as applications in the industry scale.
Okay, cool. Thanks for the question.
And we also have a related question. What's the rough order of magnitude in terms of runtime and memory usage you save by sparsifying the graphs? I guess, I'll just go.
Yeah, so I'm sorry, but I don't have the numbers off the top of my head, so I don't have a good answer to that. Yeah, that's yeah. I guess, but the motivation here is both in terms of the perhaps possibility of making things more efficient, but it's also interesting on its own behalf. I guess this is also, we're not the first one which have looked at sparsifying graphs. It's interesting to see both that you can do it and maintain still a high accuracy. And yeah, then it's a question how far you can push this in terms of the efficiency that can get out of this.
Cool. I think then we're through with the questions, unless someone else wants to throw in the last second one. And yeah, then a final thank you from my side. And maybe if you have some last words, then feel free to say them.
Yeah, just thank you very much, everyone, and for organizing this wonderful reading group. And yeah, hope to see you perhaps at a future conference.
Okay, another paper nicely discussed. And with that, I want to invite you to come to our next discussion next week. And all the information for that, like the links to our reading group, our Slack channel, and the mailing list where you can, for example, get notified about the paper that's coming up next week, or yeah, whenever the next paper is coming up. And yeah, I hope to maybe see you in those discussions. So either see you in the video next week or really in the discussion. Bye.